Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be finishing Chapter 13 on Principal Component Analysis, and we're focusing this time on why Principal Component Analysis is a sensible variable reduction technique, how to use it, how it can get you in trouble, and then I'll show you an example of using this for the purpose of multiple regression. So I haven't given you a lot of insight yet into why PCA can be used for variable reduction, so I'm going to provide that insight now. So here are two plots. Let's focus on the one on the left initially, and this is like the plot I gave in my first example for temperatures. We've got two variables here, feature 1 and feature 2 on our axes, and imagine we have a set of data whose pattern is represented by this ellipse. This blue dot represents one observation in that data set. Its coordinate in the original features is 0.99, roughly 1 along feature 1, and about a third in feature 2. That's its coordinates. When we perform principal component analysis, we create these new axes. So this first green axis in the positive slope direction is principal component 1. It's going from tip to tip along the long direction of the data. That's the direction of most variability. The widest variance is in that direction. Principal component 2 is orthogonal or perpendicular to that first component, and it's then capturing the direction of least variation, the shortest direction across the data. When we look at the data in on the axes of the principal components, and so we're basically doing a rotation of the axes. These green axes are going to rotate downward, and the principal component 1 axis is now in the right plot, the horizontal axis, and then we have principal component 2 on the vertical axis. Our data now is oriented in that direction, and here's the original point. The scores of the principal components give the coordinates on the PCA axes. This value now is at value 1 along for principal component 1, and value negative 1.3 for the second principal component. The lines that I've drawn on the left plot are the same as the lines in the right plot. We're looking it's oriented into the new axes. I have some comments down here, and I'm going to summarize them as we look at the plot. So why is it sensible to look at principal component 1 as being the most important component? So here's the reasoning. This line, this green principal component 1 axis, is not the same as doing least squares. So you can imagine treating feature 2 as the response variable and using feature 1 as a predictor variable and fitting a least squares line. If you fit that line, it will actually be a bit shallower. It'll be a bit closer to horizontal than the principal component 1. But that least squares line gives you a conditional prediction. It's the line that predicts feature 2 best when you know feature 1. So when you have a least squares line on this plot, you can plug in a value of x, feature 1, and get a good prediction for feature 2. Equivalently, if you were to swap these two features on the axes and you treated feature 1 as the response variable, y, and treat feature 2 as the x variable, the predictor, and fit a least squares line, you would get a line that best predicts feature 1, given that you know the value of feature 2. Well, what principal component 1 does is it gives you the best prediction of both of them simultaneously. And so this line, this green line, will give you the best prediction of both values simultaneously. Okay, I said exactly the same thing. And of course, this generalizes to more than two components. In fact, if so the first K principal components will give you the best prediction on the original P features among all possible choices of K linear combinations of those features. Basically, you're capturing the most information with those first components. All right, so that's basically all that says. But I gotta give you some warnings. PCA is often abused and not carefully considered when it's being applied. And I would warn against treating PCA as a catch-all technique for doing variable selection, though there are actually many situations where you can sort of blindly use it and often be okay. But in general, this is not a safe strategy. So I'm going to give you two extreme examples. Here's a plot which has two groups. On the in the upper left, we've got group 1, and in the lower right, we've got group 2. If you were to compare these two groups just using feature 1, the horizontal axis, you can see how much overlap both of these groups have in feature 1. You may not be able to detect a difference in these two groups if you just use feature 1. Similarly, if you use feature 2, there's some overlap up and down, maybe not quite as extreme as for feature 1, but there's still some, and you may not be able to really detect a difference in feature 2, or you detect a fairly small difference. So now imagine we apply principal component analysis, and along the horizontal axis, or sorry, this thick green axis here, we've got principal component 1. It's in the direction of the highest variability, treating group 1 and group 2 as sort of one single data set. It's still longer along the positive sloped direction. And then principal component 2 is orthogonal, going in this direction. So if we do a rotation now and look at just the principal components, here's principal component 1 along the horizontal axis, and now these two groups overlap perfectly. You have lost the ability to distinguish these two groups at all. So if we retain only principal component 1, doing dimension reduction, basically by ignoring principal component 2, we now have lost the ability to distinguish the groups, because it's in the direction of principal component 2 that defines the difference between the groups, up and down. Up and down, these two groups don't overlap at all. Group 1 is entirely positive, and group 2 is entirely negative. So dimension reduction in this case is disastrous if we're interested in finding differences between the two groups. That is pretty much what that set of paragraphs says. Here's an example where actually it works out just fine. So here we've got two groups, but their orientation is quite different. In fact, it turns out in this example that feature 1 would distinguish the groups perfectly, as would feature 2. And here's the direction of principal component 1 along the long direction of the entire data set, and principal component 2, orthogonal to that, actually explains very little variability across that line on the negative sloped direction. If we rotate now into the principal component space, principal component 1 actually distinguishes the groups even better than it does in terms of the original feature 1 or feature 2. In fact, it does the best. And it's this best rule, basically principal component 1 equaling 0, as giving you a distinction between these two groups. That's what we're going to see in a later chapter on discriminant analysis, where we find a best rule to distinguish groups. And that rule is a line or a plane that separates the groups in that high dimensional space. If I scroll up for a moment to the previous example, the best discriminant rule is effectively principal component 2, this line that separates those two groups. All right, I'll scroll back down. My last comment, you know what, I should say, ignore that. All right, my last comment is on using PCA for outlier detection. There's times when you have an observation in a data set, as in the plot to the left, that doesn't look like an outlier in any individual dimension. For example, in feature 1, feature 1 basically goes from the range of this elliptical data set, of which this blue point is the outlier in question. The data set basically goes from like -1.5 to +1.5, and this blue observation is roughly at -1, so it's not extreme at all. Similarly, in feature 2, the vertical axis, the data goes from roughly, say, 1.2 up to a +1.2, and this value is like 0.8. So it's not an outlier in either of the dimensions. But if you perform principal component analysis and look at the data in the rotated space, this point now stands out a lot, figuratively like a sore thumb. You know, the data set along principal component 2 basically goes up to about 1/2, and this value is about 1.25. That will really stand out. So that's one way you can use PCA for outlier detection, effectively by just rotating your data and looking at the data set from another direction. In an earlier section of this chapter, we saw the turtle shell data plotted using the Open Graphics library, and we can rotate this data set like this. And so this PCA gives you one rotation where you can look at the data in a different direction and maybe find an unusual observation. In this case, there aren't really a single unusual observation to see, but PCA gives us that ability to look at the data from a different direction. I'm going to skip over the sparrows example, which we covered in a previous video, and look at the use of PCA for variable reduction in regression. And the main idea here is that when you've got sets of variables in your data set that are highly correlated, they're each explaining similar information. So if if variables are highly correlated, when you increase one variable, you expect the other variables to increase as well. So that high correlation means that you're not getting very much additional explanatory power by including 2 or 3 of those variables than when you could just include one. So the idea here is that if we can take those highly correlated variables and collapse them using a linear combination to a single variable called principal component 1, then we can use that single variable in our regression model and reduce the number of variables we include in the regression model, but still retain a high proportion of the total variability of all the variables. So let's go back to 1928 and 29 in Berkeley, California, when the Berkeley Guidance Study was monitoring children who were born there. And this is actually a longitudinal study, so that a set of children were measured at age 2, at age 9, and at age 18. And different measurements were taken of them at those different times. The data set includes an ID number, just to identify who they are. Then we have their weight and their height when they're 2 years old. At 9, we also have their weight and their height. And at age 18, we have their weight and height. At those second 2 time points, we included 2 additional measurements. We've got their leg circumference and a measure of their strength. And we have the same thing when they're 18. So in some ways, leg circumference, yeah, that's going to be related to weight and height in some way. We have this additional variable, soma, and the somatotype is a 7-point scale, which is a person's measure of fatness. I'm not even aware that this type of measurement is used anymore. This is based on a photograph of the person when they were 18. And, this was studied in 1928. We probably use other ways of assessing this these days. For example, something like the BMI, the body mass index, which is not a great measurement either, in my opinion. So we have data on 26 boys. We'll read that data set in, and here's all those variables. They're all numeric. You can see that we've got lots of measurements for each individual. The ones we care about, 2, 4, 6, 8, 10, 11 measurements. So our hope here is to reduce this from 11 down to a smaller number of predictors to be used in a regression model. Let's start off by plotting the data, and I'm going to zoom out a bit, and I realize this is going to be a little hard to see in my video presentation, so I just remind that you've got access to these slides from the website. What patterns can we see here? A little bit hard to see. There's some correlation numbers in the upper right, and all the scatter plots are on the left. Generally, we see as people get older, their heights and their weights tend to start correlating more. So let's take a look at maybe this one plot here. LG, this is the leg circumference versus the weight for a person who's 18 years old. Let me show you another way to visualize this data. Sometimes a simplifying visualization can make a big difference. Something that we do see in this plot is that there's some outliers, right? Sort of a couple extreme observations relative to others. So basically the ones that appear in otherwise blank space all by themselves, like this person. But let's look at sort of a more simple version. And this is really just to show you an example of a different type of plot. Now, I have a function in the R code that I don't echo to the output here because it's a long function. But I define it, and it's called my.plotCore. And it creates this plot. I'm not going to discuss the code for it, but we'll sort of just give an idea of what the plot is doing. It looks similar to the plot before, except the data are replaced with ellipses, and the data here are actually triple encoded in this plot. We have the correlation number, so that's one summary of the data. Let's look at a particular one. How about this 0.91? The second encoding is the shape. So the shape of this ellipse is for a standard normal bivariate, I should just say a bivariate normal distribution with correlation 0.91 would have this shape. And the third encoding is the color. Blue here is a positive correlation, whereas the reds indicate a negative correlation. So we've overdone it here in terms of plotting and encoding our data, but it gives us a very quick way of looking at which variables are highly correlated and which are not. So one thing that I see is the heights and the weights for 9-year-olds. That's this one here is pretty highly correlated, and the weight and the leg measurement is really highly correlated. It's at 9 years old and also at 18. This is the weight versus the leg circumference. And generally speaking, there's lots of variables here that are positively correlated. So we can probably get away with some dimension reduction. Let's take a look at the choices that I made. I looked at just the correlations of all the weight measurements, weight at 2, 9, and 18, and saw that they were pretty highly correlated with each other. Similarly for heights, and then I put the leg and the strength measurements all together. And if we look at certain pairs of variables, so the weights at 2 and 9, 2 and 18, and 9 and 18, these are all the weight variables up at the top. Those are those positive relationships. The next three are the height at the 3 time points, and especially at 9 and 18 we see a strong correlation here. So it seems that once you get to be an adolescent, the relationship of your height is strongly predictive at that point to how tall you'll end up being as an adult. And here is the correlation between the leg circumferences at 9 and 18. So if you've got big legs when you're 9, you'll have big legs when you're 18, basically. And then here's the strength measurements, except for this one poor person who was really weakling when he was 9 years old, but then turned out to be quite a bit stronger at 18. Everyone sort of clusters here. It's this minor positive correlation. All right, so I have tons of output here, and I'm going to discuss the computer output and hit some of those points above, and I encourage you to read those. So what I'm going to do is I'm going to perform principal component analysis on just the 3 weight variables. And let me zoom back in now. The first variable here captures 67% of the variability, and the component loadings are all negative. So that's generally how strong is this is about weight. How heavy is a person throughout their growth period. So component 1 basically describes that people who are low weight when they're at 2 years old tend to be low weight throughout their lives. And then same thing with high weight people. The second component gets us up to 94% of the variability in weight. And this is a contrast between people who were, say, heavy when they were at 2 years old, but then light in later years, or the other way, someone who is, which way did I say it the first time? This is maybe light when they were young, but then gained a bit of weight in their adolescence and kept that weight. That's the second component. Let's look at the height principal components. The first component here, again, is all positive loadings. So that's generally just how tall someone is. If you're born tall at 2 years old, say, if you're tall when you're 2, you tend to be relatively tall when you're older. That's the first component, and that explains 85% of the variability. If you add a second component, you get 10% more, and you're up to 96% of the variability, and that's the difference between being short when you're young, but then having growth spurt and being tall, or starting off long, but not growing very much once you hit adolescence. That contrast. The last 2 PCAs looks at just the leg circumferences, and the first component has the same sign, so that's just generally how big your leg is, explains 83% of the variability. So we're getting pretty much of the variability in one component. And for strength, same thing. Our strength variables, loadings, both have the same sign, so that's generally how strong you are at 9 versus in 18. If you're strong when you're young and strong when you're old, those tend to correlate with each other, and that explains about 83% of the variability. So one strategy that you can use at this point is you can select certain principal components to use in a regression model rather than the original correlated variables. There's several advantages to that. One main example, if I just go up to the weight variables for the descriptions here, is these 3 components, components 1, 2, and 3, are they're uncorrelated with each other because we have reoriented the data. If I scroll up to a picture, here's a picture. In our original features, feature 1 and feature 2, we had this positive correlation. We had this sort of positive slope of our data. Once you perform principal components and do this rotation, now you no longer have any slope in your data. And so these two variables are now uncorrelated. That's a great thing for a regression model because when you interpret regression coefficients, we want to know, right? So what's the interpretation of beta 1, a slope parameter associated with x1? It's the expected increase in your response for each unit increase in x1, conditional on all the other variables staying the same, staying fixed, not increasing. If you include, in this case, both features 1 and feature 2, it's hard to increase feature 1 without feature 2 also increasing. So it hurts our interpretation of that beta coefficient. However, when we interpret principal components, you can increase principal component 1 without increasing principal component 2 at all. Furthermore, if principal component 2 doesn't even include very much variability, don't include it at all. Just include principal component 1. So we get those two benefits from using PCA, provided, let me page down a bit, provided, of course, that it's pretty straightforward to interpret these components, the loadings. So in this case, the first component is generally the size, the weight of a person over their lifespan, over their growing years. And that's a fairly straightforward component to interpret. So I will say, if I page up a bit, I've got several paragraphs here, and I encourage you to read through, but I've hit most of the main features in this discussion. And that completes Chapter 13 on PCA.